Hello, this is Dr. Brown. In this video we're going to talk about antiderivatives, and this will lead us into the second part of this calculus course, which we will call integral calculus. Now, integral calculus will help us do things like calculate the area under a curve. Suppose this is f of x, and we want to find the area under the curve from x equal a to x equal b. And if it is not any kind of regular geometric figure like a rectangle or a triangle or a trapezoid, we need a new way of calculating the area under the curve, and that's what integral calculus will do for us. And the key to this is to be able to find the antiderivative of a function. Now, we're going to define what an antiderivative is here. A function, capital F, is an antiderivative of the function lowercase f on an interval I if the first derivative of capital F is equal to f of x for all x on the interval. Now, to give an example, suppose f of x was equal to cosine of x. The question is, what function has a derivative cosine of x? Well, capital F of x equals sine of x is an antiderivative of cosine of x because, as you well know, the first derivative of f of x, which is the first derivative of sine of x, is cosine of x. Now, we also know that f of x could also be sine of x plus a constant, because the derivative of a constant is 0. So we say if f is an antiderivative of f on an interval I, then the most general antiderivative of f is capital F of x plus a constant, where c is an arbitrary constant. Now, let's do some examples. Suppose you wanted to find an antiderivative for each of these following functions. So the question is, 2x is the derivative of what function? Well, that would be capital F of x equal x squared. You just sort of work backwards, plus a constant, of course, because taking the derivative of capital F of x is just 2x plus 0, which agrees with lowercase f of x. Now, the second one here, we know that capital G of x would be sine of x plus a constant, because g prime of x is cosine of x. You can always check if you have the correct antiderivative by taking the derivative of the antiderivative and seeing that you get the original function. Now, let's look at lowercase h of x and figure out what function h of x, uppercase h of x, would have a derivative equal to 1 over x plus 2 e to the 2x. Well, you know that the function ln of the absolute value of x has a derivative 1 over x, so that would take care of that part. And you know that the antiderivative, or the derivative of e to the 2x, is equal to 2e to the 2x. So if we add a constant, we have the most general antiderivative of 1 over x plus 2 e to the 2x. Now, let's look at another one. Suppose you had lowercase f of x equal x to the n. What is the antiderivative of x to the n? Now, you already know that the derivative of x to the n is n x to the n minus 1, so we want to sort of work backwards and play around with this. We sort of know that the antiderivative would be x to the n plus 1 power, because when we take the derivative, we're going to reduce the power by 1. But when we multiply by n plus 1 and put it here to take the derivative, we'll be off by a factor of n plus 1. So you could see that what we need to do is take x to the n plus 1 over n plus 1. So this is the power rule for an x to a power. So it's x to the power plus 1 divided by the power plus 1. Now let's find the antiderivative f of x of lowercase f of x equal 4x to the third power. That satisfies the condition that f at x equal 1 equal 3. Well, let's do that. Capital F of x would be equal to 4 x to the power plus 1 over the power plus 1, which would be 4x to the fourth divided by 4 plus a constant. And that would be equal to x to the fourth plus a constant. Now, to figure out what the constant is, we need to use the information that's given to us, that f at 1 is equal to 3. So f at 1, which would be 1 to the fourth plus a constant, if that's going to equal 3, we get the equation that 1 plus c equals 3, and that c is equal to 2. So the function of x that we're looking for, the particular function, is x to the fourth plus 2. Now on the next page, we have the function y equal x to the fourth plus a constant for various constants. I've graphed them here, and you can see the graphs all look the same except they are offset by a constant. And the one that we just calculated was for c equal to 2. Notice that it satisfied the condition that f at 1 would equal 3. And notice that all of these functions at a given point have the same slope for the tangent line. In fact, all of these functions differ by just a constant. Now, let's look at a lot of other antiderivative formulas. You can think of a lot of antiderivative formulas just by knowing that if you have f of x and know its derivative, f prime of x, you can find its antiderivative by going backwards through the table. For instance, x to the n has an antiderivative of x to the n plus 1 over n plus 1 plus c. The antiderivative of sine of x would be minus 1 over k cosine of kx plus a constant. Notice that you're dividing through by k, where k is a multiplier on the x, and obviously the derivative of cosine is minus sign, and then using the chain rule, multiplying by k, you arrive that the derivative of the antiderivative is indeed sine of kx. The antiderivative of cosine of kx is 1 over k sine of kx plus c. You remember the derivative of tangent of x is secant squared of x. So we can develop the antiderivative table that the antiderivative of secant squared of kx is 1 over k tangent of kx plus c, and you can go on through the table and develop a number of general antiderivatives for the various functions. And you will be using this table throughout the rest of this course. Now, let's find the antiderivatives of each of the following functions. Number A, if f of x is equal to x to the fifth, then capital F of x, using our power formula, will be x to the 5 plus 1 over 5 plus 1 equals x to the 6 over 6 plus a constant. Now, to find the antiderivative of lowercase g of x, we would write that g of x is equal to x to the minus 1/2 power. And then using the formula, capital G of x would be x to the power plus 1 divided by the power plus 1 would be equal to x to the 1/2 divided by 1/2, which then again would be 2 square roots of x plus a constant. For C, where h of x is equal to sine of 2x, the antiderivative would be minus cosine of 2x over 2. Notice you would use the formula on the previous page where k is 2, and you would add a constant to get the general antiderivative. Now, problem D, I of x is equal to cosine of x over 2. Here k is equal to 1/2, so the antiderivative, the general one, would be 2 sine of x over 2 plus a constant. Continuing for E, for j of x equals e to the minus 3x, capital J of x, its antiderivative would be minus e to the minus 3x divided by 3. And then finally, F, if k of x, lowercase k of x, is equal to 2 to the x, looking at formula 8, capital K of x, the general antiderivative would be 2 to the x divided by ln of 2 plus a constant. Now on this page there are several rules about antiderivatives. I think you've already probably picked up the fact that if f of x is equal to cosine of x, then capital F of x is equal to sine of x. If f of x were equal to 1/4 cosine of x, then capital F of x is just 1/4 sine of x. That's called the constant multiple rule. If you want the antiderivative of k times f of x, just take the antiderivative of little f of x and multiply it by k. The negative rule is pretty obvious. If you want the antiderivative of minus f of x, take the antiderivative of f of x and multiply it by a negative. And then finally, the sum and difference rule. The antiderivative of f of x plus g of x is just capital F of x plus capital G of x, and the same goes if it's a difference. For instance, suppose f of x is equal to x to the 8th minus 3e to the x. Then the antiderivative is the antiderivative of x to the 8th, which is x to the 9th over 9 minus 3e to the x. Notice the antiderivative of e to the x is e to the x. Next, we're going to show how we use an antiderivative to solve some motion problems. These are called solving some very simple differential equations. We got a case here where a balloon is ascending at a rate of 12 feet per second, and it's at a height of 80 feet above the ground when a package is dropped. How long does it take the package to reach the ground? Well, we start out with some fundamental facts that we already know. We know that the acceleration of gravity, which is dv dt, on Earth is minus 32 feet per second. Now, if dv dt is equal to minus 32, we could also write that v prime is equal to minus 32. To get to v and solve for it, we take the antiderivative of minus 32. So v would be minus 32t plus a constant c1. And we want to now find c1, and we use the initial condition that v at t equals 0 is equal to 12. That comes from the information given in the problem. So v at 0, plugging in 0 here, we get minus 32 times 0 plus c1, and that is equal to 12. Solving that for c1, we get c1 is equal to 12. And so we come up with the equation that v of t is equal to minus 32t plus 12. Now we want to find an equation for the position s of t. We know that v is equal to ds dt. Well, ds dt we just figured out was minus 32t plus 12. So finding the antiderivative of ds dt, we can calculate s. So finding the antiderivative of minus 32t plus 12, we get that s must equal to minus 16t squared plus 12t plus another constant we're going to call c2. Now we're given that s at 0 is equal to 80 feet. In other words, the package is dropped from a height of 80 feet. So S of 0 is equal to minus 16 times 0 squared plus 12 times 0 plus C2, and that equals 80. This implies that C2 is equal to 80. So now we have a full equation for the position, which is minus 16 t squared plus 12t plus 80. And so we want to find how long it takes the package to reach the ground. Well, when it reaches the ground, S equals 0. So we want to set S equal to 0 and solve for t that makes that so. So looking at this, let's divide by 4, and we get minus 4t squared plus 3t plus 20 equal to 0. Notice that this is a quadratic equation, and we can't factor it easily, so we can use a quadratic formula where a is equal to minus 4, b is equal to 3, and c is equal to 20. And so t, using the quadratic formula, is minus b, which is minus 3, plus or minus the square root of b squared, which is 3 squared, minus 4 times a, which is minus 4, times c, which is 20, all over 2a, which is minus 8. And you can see this is minus 3, plus or minus the square root of 329, divided by minus 8. And you've got two solutions. One is a negative solution, which is not one of the solutions we're looking for, because that would be before the package was dropped. Anyway, we get minus 1.89, and we throw that one out. But the other one, which is positive, is t equal 2.64 seconds. Tells us that the package hits the ground after 2.64 seconds. Now on the next slide, we're going to introduce some notation, and it's the integral sign, which looks like this. And the definition is a set of all antiderivatives of the function f. It's called the indefinite integral of f with respect to x, and it's denoted by the integral of f of x dx. The symbol given here is an integral sign. The function f is called the integrand of the integral, and x is called the variable of integration. So let's calculate the antiderivative of x squared minus 2x plus 5. That's exactly what this means. Having this followed by d of x and some function of x simply means that equals the antiderivative of f of x, of f of x plus a constant. So this is equal to x cubed over 3 minus x squared. The antiderivative of 5 is 5x plus a constant. Notice you can write down a lot of indefinite integrals. Antiderivative or indefinite integral of cosine of x dx is equal to sine of x plus a constant. The antiderivative of secant squared of x dx is equal to the tangent of x plus a constant. Why? Because the derivative of tangent of x is secant squared. And so you could go on and on. And this simply means take the antiderivative of little f of x. Now, the last two problems are going to relate to rocket science. This is a very simple example in which a rocket is fired with an initial velocity of 1,500 feet per second. It's fired vertically from the Earth at t equals 0. In this particular example, we're not going to continue to burn the rocket. We're going to give the rocket initial velocity of 1,500 feet per second. And it's going to continue to rise until gravity brings it down and it hits the Earth again. If the engines had kept running, it would have kept obviously gone into orbit, or if it had been going with a lot of acceleration, it could have actually left the Earth and headed, for instance, to the moon. That's what happened with our first Saturn V launch back in about 1968 when we went to the moon. This particular case, we're just going to go up a few thousand feet and come back down. But anyway, a rocket's fired vertically from the Earth with an initial velocity of 1,500 feet per second. Using the fact that the acceleration of gravity is minus 32 feet per second on Earth, calculate the following: the number of seconds a rocket ascends before falling back to Earth, the maximum height the rocket attains before descending, the time when the rocket returns to Earth, and the velocity of the rocket when it hits the Earth. Well, it turns out that this is going to be very similar to a problem that we just worked, with just a few more things that we want to solve for. But we start out fundamentally with the fact that the acceleration is minus 32. Since dv dt then is the acceleration is minus 32, we take the antiderivative just like we did before and get v equal minus 32t plus c1. And since v at 0 is equal to 1,500, we get that minus 32 times 0 plus c1 equal to 1,500. So c1 is equal to 1,500. So now we have an equation for the velocity, which is minus 32t plus 1,500. Now, we know that the rocket is going to continue to rise until v equals 0. Now, v equals 0 at solving this for t, we get t is equal to 1,500 divided by 32. And that is 46.875 seconds. So the answer to the first question is the number of seconds a rocket ascends before falling back to Earth. It ascends until the velocity is 0, and that's at 46.875 seconds. Now, we want to now calculate the maximum height of the rocket, so we have to solve for s. Since ds dt is equal to the velocity, ds dt then is minus 32t plus 1,500. Taking the antiderivative of ds dt, we get that S is minus 16 t squared plus 1500 t plus a constant C2. Now, to solve for C2, we know that S at 0 is equal to 0. In other words, it starts on the ground. So we get minus 16 times 0 squared plus 1500 times 0 plus C2 equals 0. So C2 is equal to 0. So now we know that the position S of t is equal to minus 16 t squared plus 1500 t. And we can find the maximum height the rocket attains by calculating the position at t equal to 46.875. That's when it starts falling back to Earth. So S at t equals 46.875. We just plug in S at 46.875 is equal to minus 16 times 46.875 squared plus 1500 times 46.875, and calculating that we get 35,156.25 feet is how far the rocket goes before it starts falling back. And then we want to find the velocity of the rocket when it hits the Earth. Actually, we want to find the time when the rocket returns to the Earth. That's when S is equal to 0 again. So we have to solve for minus 16 t squared plus 1500 t equals 0. And we can factor a t out and get t times minus 16t plus 1500 equal to 0. And t is equal to 0. That's when it leaves the Earth, and it comes back to Earth at t equal to 1500 divided by 16, which is 93.75 seconds. So that's the time of return. So it stays up for about 93.75 seconds. And on the next page, we're going to use the velocity equation, which is minus 32t plus 1500. To calculate the velocity when it returns, we have to plug in t equal 93.75, and we get minus 32 times 93.75 plus 1500. Doing the calculation, you get minus 1500 feet per second is the velocity when the rocket hits the ground. Notice it goes up with an initial velocity of 1500 feet per second. It hits the ground with a velocity of minus 1500 feet per second. And that's the rocket equation. Now it's your turn. I'd like for you to pause the video and work a problem very similar. A rocket is fired vertically from a small planet with an initial velocity of 1500 feet per second. Now, using the fact that the gravity on the smaller planet is only 10 feet per second, calculate the following. The same things as we calculated before, except you'll do it on a smaller planet. Now, if you do this correctly, you should find out that the velocity will end up being minus 10t plus 1500. The position will end up being minus 5t squared plus 1500t, and the number of seconds the rocket ascends will be 150 seconds. The maximum height the rocket attains before descending will be 112,500 feet. And the time when the rocket returns is at t equal 300 seconds. And the velocity of the rocket when it hits the planet again will be minus 1,500 feet per second. So I would suggest that you work out and make sure that you can get these numbers.